So you'll notice that there are some different elements here, different isotopes, undergoing different alpha and beta decays. Now, if you look on the left-hand side here, you'll notice something called half-life. And each of these elements has its own unique value for a half-life. What a half-life is, it's the amount of time it takes for half of the parent material to transmute into something different. Or for my sample, to have half of my remaining sample remaining. So for example, if I have uranium-238 and I start with 100 grams of that, it's going to take 4.5 times 10 to the 9 years to leave me with 50 grams of uranium-238. If I look at something with a shorter half-life, like radon-222, it has a half-life of 3.83 days. So if I start with 500 grams of radon-222, after 3.83 days, I'm going to have 250 grams remaining. After another 3.83 days, I'm now going to have 125 grams remaining, and on it goes. So half-life is the amount of time it takes for half of my sample to transmute into something else. Now, if we were to look at that graphically, it would look something like this. If you notice on the x-axis, though, we have number of half-lives. It doesn't have to be just number of half-lives. I could also plot activity on the x-axis, and I would end up with the same curve. Activity is the amount of decays per second, measured in something called a becquerel. If you think about a movie, whenever they have Geiger counters in the movies, that click that you hear is an example of the activity of a substance. And that's based off of the amount of parent isotope that's present, so the graph would be the same shape. On the y-axis here, we have percentage of parent isotope remaining. We could have an amount in grams, kilograms, it doesn't matter. We'd still have that same shape. Now, based off of that shape of the graph, we have this equation. So it's a logarithm. However, we don't need to be really good with logarithms to understand these types of questions. This is a very simple calculation that allows us to identify the amount of a sample present after an amount of time has passed. So for this example here, if I start with 765 grams, it's my original amount, I multiply that by half to the power of the number of half-lives. Now here, we're looking for how much is remaining after 3.8 years. 3.8 years is not the amount of a half-life. A half-life is 138 days. However, I can do some simple calculation. 3.8 years times 365 is 1,387 days. Divided by 138 days per half-life gives me 10.05 half-lives. So I can calculate this. I can go to my calculator now. 765 times 1/2 to the power of, and my answer is still there, so I'll put that in there. I get 0.72 grams. So 0.72 grams is the amount of sample remaining. Now, this next question is where we might need to require, where it might require a more advanced understanding of logarithms. However, we can answer these types of questions with just a simple understanding of what a half-life is. I have 75 grams, and I want to find out how many half-lives have occurred when 9.38 grams is remaining. Well, I can use my calculator, and just understanding that a half-life is the time it takes for a sample to divide in two, well, after one half-life, I'm going to have 37.5 grams remaining. After two half-lives, there's going to be 18.75 grams of sample remaining. And after three half-lives, I'm going to have 9.38 grams. So that's 3 half-lives to go from 75 grams to 9.38 grams. So it's 3 half-lives. Now, if each half-life is 10.6 hours, after 3 half-lives have occurred, well, I can calculate how long that'll take. 10.6 times 3. And to 26 figs, that's 32 hours. So it would take approximately 32 hours for 75 grams of lead 212 to decay into 9.38 grams of sample. So again, the definition of a half-life is the amount of time it takes for a sample to transmute into half of what I started with.